Hello everyone. So previously we had discussed on the topic subset sum or partition algorithm, right? So today we'll be discussing on the topic coin change algorithm or the problem, right? So this is one of the famous problems within the DP. If you would have solved the problems on the DP, this is one of the famous problems that can be solved with a DP, usually solved with a DP, right? So yeah, let's get into the definition part. Let's see what the definition says here, right? Using given coins, see here, coin change refers to the problem where we must form a target amount using the given coin denomination. Sorry. Again, coin change refers to the problems where we must form a target amount. So there will be some target amount given, and we have to make up to that target amount using the given coin denominations. Yeah. So usually you would have heard of this one. Coin change or something, the same problem name in the LeetCode, right? 1 and 2. If you would have solved, you would have known the one of the famous problems that can be solved using the DP actually. Yeah, coin change refers to the problems where we must form a target amount using the given coin denominations. There are two common variants. One is count the number of combinations. How many number of combinations are there? We have to count the number of combinations. Order doesn't matter here, just to make the amount, right? That sum ups to the amount actually in simple terms, right? So we have to find the minimum number of coins required to make the amount, or we have to report impossible if it is impossible to this one sum up to the amount, right? So this is fine, I believe. Next, let's get into the explanation part. Both the variants are classic dynamic programming problems, right? So we'll be making use of similar to the unbounded knapsack style. So this one actually before the subset sum or partition algo, we discussed about the unbounded knapsack algorithm as well. Yeah. Uh, so we have the idea on the unbounded knapsack, right? So we have the idea on the unbounded knapsack, right? So here both the variants are classic dynamic programming problems because each coin can be used repeatedly. So we can make use of the coins repeatedly actually. Suppose we have been given one, two coins, one, two, and the so simple example here. See, we have been given suppose coins 1 and 2 and target amount. So let me consider here amount for the target amount. So target amount, let's say it's actually 10, right? So we can this is actually we can use this n number of times, right? So here that basically sums up to the target amount. So we can just make use of the this one. Suppose it's 1 rupee and 2 rupee coin. As we live in India, let's consider rupee actually. Yeah. So this one, let's consider 1 rupee coin 10 times. 1 plus 1 plus 1. So it will be 10 coins. This will lead to the this one. Target amount. Also, we can go with a this one. What do we call? Uh, 5 2 rupee coins as well. 5 2 rupee coins as well. That is also one of the thing, right? So that will also lead to the target amount 10. Or we can just make use of this one, two this one 1 rupee coins and four this one 2 rupee coins. That is also one of the combinations. That there are many combinations, right? Uh, Similarly, I'll just write this one similarly. Right, so this is what they are saying actually. Both the variants are classic dynamic programming. This one dynamic programming problems because each coin can be used repeatedly. For counting combinations, we will be making use of 1D DP array base. 1D DP array way. This one base of S, where base of 0 is equivalent to initially 1. Right. So and for each coin, iterate sums from coin to amount doing base of S. Equals base of S plus base of S minus coin. So this is what we will be going with. Just remember this one. This is very important, right? So however, you will come to know while we write the code or while we write the algo, right? So iterating coins in the outer loop ensures combinations, right? Not permutations. So if we have solved this problem very recently, coin change 1 and 2, if you remember. So we'll be going with the two for loops, right? We went with the two for loops actually, if you remember, right? So for minimum coins, let's use dp of s that is initialized to infinity except dp of 0 equals 0 and update the dp of s equals min of dp of s comma dp of s minus coin plus 1. So this is what we'll be doing. So this one I'll just explain this one while writing the code itself, right? So just you have to know before writing the code. That is the reason I'm just explaining this. Again iterating this one, again iterate coins outer. sums inner to maintain the correct unbounded behavior, right? So this is fine, I believe. Yeah, let's do one thing. Yeah, let me come out of this one. What do we call? Not come out of this. Basically, let's move on with the further things. Let's start writing the algo. There are two variants, right, to solve this problem, coin change. So one is counting the ways to make the target amount, and another one is minimum number of coins required to make the amount, or minus one if it is impossible. Let's go with both the variants. First, let's go with the counting ways to make the target amount. So I'll just give here def coin change. Let me give here count. So let me go with two parameters. One is I need coins and another one parameter I just need amount. So within this function, so let's go with a base of I that will hold the number of ways to this one. Make some I. In simple terms, I'll just initialize base with uh, 0 to amount plus 1 actually. Amount plus 1. So this is fine. Yeah, next let's go with the base case that we discussed. Nothing but there is one way to make 0, nothing but choosing nothing, right? So I'll just go with base of 0, nothing but this is the base case. Let me assign this one to the 1. Next we have to iterate through each coin, right? So this is unbounded is allowed here. Unbounded use allowed in the sense. So this is exactly similar to the unbounded knapsack. Any number of this one, unlimited usage is allowed in simple terms, right? That's what we saw in this one. What do we call unbounded knapsack as well. So we can consider only one thing at a time in normal this one knapsack 01. In the unbounded knapsack, unlimited usage was allowed, right? Unlimited usage was allowed. So here we will be iterating through each coin. So here again unbounded usage is allowed, right? So I'll just go with for C in coins. So let me go with here for uh, S in the range. For S in the range, I'll just go with C, comma, amount plus 1. Amount plus 1. So within the for loop, let's go with base of S equals base of S plus base of this one, S minus C. This is fine. Yeah. Finally, what we need to do, we have to um, return the full table for the explanation. Also, we need to return full table for explanation. So I'll just go with a return base of amount, return base of amount, comma, base, comma, base. This is fine. Yep. This is it for the coin change count function actually. Yeah, this is the first variant actually. We are successful in writing it. Next, let's go with a second variant. Nothing but the same problem can be solved with this one. What do we call? By calculating the minimum number of coins that is required to make the amount, or let's display minus one if it is impossible to sum up to the account, right? Amount, sorry, not the account, sorry. Let's write the another variant. I'll just go with def coin change man here. So let me go with the same parameter, coins and the amount. So usually we make use of the second one actually, the two for loop. So we solved with the same using the Java. So if you remember, right? So dp of I here, it will hold the minimum coins that is needed to make some I, right? So let me make use of the infinity here, infinity value. Let me assign this one to 10 to the power of 9, exponent operator 9. Yep, this is fine, I believe. Next, let's initialize with large number, meaning which represents the infinity. So this one will be dp equals infinity uh, into amount plus 1. So this one amount plus 1. Yep, the base case, let's go with the 0 coins that is needed to make some 0. So this one will be dp of 0 equals 0. Yeah, uh, let me go with this one. Let's move on with the iterating the coins, meaning let's iterate coins. This is unbounded. So I'll just go with for C in coins. So this is fine for C in coins. So for the sums that can include coin C, that one also we have to check, right? So I'll just go with one more for loop for S in range. Range, I'll just go with C, comma, amount plus 1. Yeah. So yeah, this is similar to this one. Yep. Now let's do one thing within the for loop. So either we don't use coin C, nothing but dp of s, or we will use it once plus best for s minus c, nothing but dp of s minus c plus 1. We know this. Let's write the simple if condition for that. So I'll just go with if here. If dp of, I can just write it in this way, s minus c plus 1, if it is less than dp of s, then what we'll do, dp of s equals dp of s minus c, this is also fine, plus 1. Yeah, this is fine. Next, let's do one thing. If it is impossible, then we'll then let's this one return minus 1 and also the table, right? So I'll just write return here. What we need to return? Minus 1 if dp of amount, if dp of amount, um, if the dp of amount is greater than or equal to infinity, greater than or equal to infinity, else dp of amount, else dp of amount, let's go with the dp, right? So minus 1 if impossible, and we are returning the table as well. Yeah, so this is it for the algorithm one. Simple. Yeah, I have showed you both the variants actually. Yeah, so the first one is nothing but counting the ways to make the target amount. Nothing but order of the coins doesn't matter here. The second one is nothing but minimum number of coins that is required to make the amount, or we will we have to return minus 1 if it is impossible to sum up to the amount actually. Yeah, so this is fine, I believe. Yep. So now we are done with the algo. Just for the interactiveness, I'll just let's go with the example usage that I'll take from the Google Man. Just give me a second here. So I'll just come here. Let me paste this one over here. I have considered the simple example here. I have considered very simple example here. Coins I have considered, amount I have considered. Coins I have considered only 1, 2, and 5. Right? Different denominations, coin denominations. Let's consider this one 1 rupee coin, 2 rupee coin, and this one 5 rupee coin. Right? Amount that has to this one by making use of different coin denominations that we have to that uh, must lead to the this one target amount as 11 actually. 11 is the target amount that we have considered, right? So this one is fine. Count result, count table, minimum result. So this one you can just have a look into it. I'll just pause the video. This is just this one. We are calling the first function here, coin change count, coin change minimum, the second function actually. Yeah. Print, we are making use of it for the interactive purpose, right? So suppose what is the output that we need to get. So we have complete understanding of the algorithm that we have discussed now. So what is the output that we need to get accordingly with what we have written now. So here accordingly with the example usage, right? Let's discuss the same actually. So if I run the code, I need to get the output. 1 second, I'm getting a call, just give me a second here. So yeah, if I run this, initially what we are doing here, we are just printing the coins, the same thing we are printing, right? So we have to get coins equals 1 to 5. So next we are printing the target amount, see target amount, right? So we just have to get this one along with this one, coins equals 1 to 5, amount equals 11. Next, what we are printing here, number of ways combinations to make the amount, right? So this one number of ways combinations to make the amount 11. So we are just coin result we are printing. So this one 11 we have to get here, right? So dp table for the count index equals sum to this one we are printing, right? So this one, yeah, this one we are printing the dp table for the count index equals sum ways, right? So this one we have to get actually uh so it will be initially we are considering 11 here. The amount we have considered 11 and the denominations are coin denominations are 1 to 5. So the output that we need to get here is 0 ones first initially, 1 1, 2 2. So we can just write it in this way, 3 2. So this one 4 3, and we will be going with a 5 4 actually. So 6 5 7 6 here. Mm, then I'll just continue from here. 8 7 9 8, finally 10 10, and 11 11 11 11. So this is the DP table for the count. Index equals sum to base actually. So sum to base actually. Yeah, sum to base. Yeah, this one I have shown. That's what we are printing here. This one actually. DP table for the count index equals sum to base actually. This is fine. Next, what we are doing, this is for the first one actually, first algorithm that we have written, right? So let me delete this one. I hope this part is completely clear, man. First, we are just printing coins amount. Then we are just going with a this one minimum this one number of ways, nothing but the combinations to make the amount nothing but 11. So we have shown all the 11 this one, right? So we have shown using the DP table. Mainly we are showing the DP table for the count index equals sum to base. So this is fine. For the next one, so let me delete this one. Yeah. For the next one, what we are doing, we are just going with the minimum coins required to make the amount, right? So this one minimum coins required to make the amount, line number 52, right? So this one has to be 3. So minimum coins to make this one required to make to the amount, this is 3. So we are calculating the minimum amount, minimum coins that is required to make the coin, this one, to sum up to the amount 11 actually. So this will be basically by looking at it itself, you can just say, right? So we can just go with 2 5 rupee coins and 1 rupee coin, right? So this will lead to 11, right? This one will be basically we have to get the output. Minimum coins required to make the amount is 3. We need to get 5, this one, 2 5 rupee coins and 1 rupee coin, right? So DP table for the minimum coins is nothing but index equals sum to minimum coins or infinity, right? So the table we can just represent in this way: 0 to 0, 1 to 1, 2 to 1, this one, 3 to this one, 2, 4 to 2, and this is 5 to 1, 5 to 1, 6 to 2, and 7 to 2 here, this one, and 8 to 3. I'll just continue from here, 8 to 3. So 9 to 3 as well, 10 to 2, and finally 11 to 3. The final one, the last cell, the value that is present in the last cell, this one will return this one as output basically. Yeah, sorry, this one is not 13 actually, this is 3. 11 to 3. This will return this one as output. So minimum, this one coin required to make the amount actually, target amount is 3, right? Target amount is 3. 5 2 rupee coins and 2 5, sorry, yeah, 2 5 rupee coins and this one 1 rupee coin, that will lead to 11 actually. Right, so this is fine, man. Now, actually, this is the DP table. How it works, I have shown. How it works, actually, how the DP works, I have shown here. Right? So this is for the first example also, I've shown you the sum two amount ways actually, I believe. Yeah. Sorry, this one, sum to base actually. Sorry, sum to base actually. Right? Index equals sum to base. So this is the output that we need to get. So let's see what is the output that we get. Let me run. Let's see whether the algorithm works correctly or not. So I'll just give Control J here. Screen Python, Python followed by file name dot py, right? So let me go with the first one here. DP table for the count index equals sum this base, right? So this is fine, man. Yeah. So here 0 to 1, 1 to 1, 2 to this 1 to 3 to 2. So as I've shown this one, sum to base, this one, we are getting the correct output. So uh, first initially we are just displaying coins, target amount, then number of ways combinations to make the amount 11 that I've said. I've shown you actually DP table for the count. So index, this is sum to ways, this one we are printing, so we are getting the correct one. At the end we are getting 3. This is fine, not the 3 actually, 11 11, sorry, this one. And for the second one, let me enlarge this one, sorry. Yeah, minimum coins that is required to make up to the amount 11 as target amount is 3. This one we have discussed. DP table for the minimum coins index, this one equals sum to minimum coins or infinity. See here 0, this one we have already discussed, right? 11 to 3 at the end. So this one will usually will return this one as the output, the one that is present at the last cell. Yeah, this is fine, I believe. Simple one. Yeah, so we are done with the coin change algorithm or the problem. So before moving on with the next algorithm, let me summarize whatever we have learned so far, right? So let's see. Mm, so here, just try to remember these 3 to 4 points, man. The first point here, I would say, coin change has two frequent flavors here. Coin change has two frequent flavors. One is counting combinations and finding minimum coins. Yeah. counting combinations and finding minimum coins. Coin changes to frequent flavors. One is counting combinations and another one is finding minimum. Finding minimum. So yeah, finding minimum. Yeah, so usually we go with the finding minimum. Yep. Uh, this is fine. Mm, Now, the second point is both are solved by 1D DP. Both are solved by basically 1D dynamic programming. Nothing but the this one unbounded knapsack pattern. So that is the reason we have to know the 0, 1 knapsack and the unbounded knapsack clearly. We'll be making use of it this style in many problems actually. In many DP problems, you have to know the difference between the normal 0, 1 knapsack algorithm as well as the unbounded knapsack as well, right? So that is very important. Both are solved by 1D dynamic programming. Yeah, unbounded knapsack pattern with big of n into amount time and big of amount space, right? So big of n into amount time and big of amount space. So the third one here, the third point is so use the coins outer loop. So we went with the two loops, right? For both actually. Use coins outer loop and some inner loop to treat coins as unlimited and to count the combination rather than the permutations, right? For teaching this one, for this one, not teaching one, sorry. For this one, for running. So basically, for running the code, so we will be making use of the uh, basically this one DP table evolution, right? Basically, that's very intuitive type. So I have shown you both the DP tables. So I hope this is fine. Actually, I hope this is fine. So this is it for the algorithm. This is it for the algorithm, right? So next, what we'll do, we'll be discussing on the rod cutting algorithm or the problem. That is also one of the famous DP problems of the algo, right? Rod cutting algo or the problem, right? So for now, this is it. Thanks for watching, guys.